Hello, and welcome to our channel. My name is Dmitry, and I'm a part of the Exactpro research team. At Exactpro, we build software to test software. Do check out our website if you want to learn more about us. And please subscribe and hit that bell button to make sure that you see the upcoming videos. We are continuing our series based on the ISTQB Certified Tester AI testing syllabus. In the previous video, we were introduced to machine learning workflow. And we already know that the model cannot learn without data. But how do we prepare the data for the model? Today, we will review Chapter 4, called Machine Learning Data. Data preparation uses an average of 43% of the machine learning workflow effort, which makes it the most resource-intensive activity. This process takes in raw data and outputs data that can be used to train the machine learning model, and use that trained model to make predictions. Data preparation consists of the following. The first phase is data acquisition. We identify the types of data to be used for training and prediction. For example, for a self-driving car, we decide if we need a radar, video and laser imaging detection, and LiDAR data. Then we determine where and how we gather the data. And after that, we'll label the data, which can take various forms. For example, numerical, categorical, image, text, sensor, video, audio, etc. During the second phase, data needs to be pre-processed. So we need to clean it, which means that incorrect data, duplicates, and outliers are identified, removed, or corrected. Next, we replace the missing values with estimated or guessed values. This process is called data imputation. The removal of personal information may also be performed. The data is then transformed. For example, an address stored as a string is broken down, or categorical data is converted into numerical data. Operations such as standardization and scaling can be applied to numerical data, which involves reducing the data to a single range. Then comes augmentation. It implies increasing the number of samples in a dataset. And lastly, we have sampling, which involves selection of some part of the available dataset so that the patterns in the larger dataset can be observed. This is typically done to reduce costs and time. We need to keep in mind that all pre-processing carries a risk that it may change useful valid data or add invalid data. The last phase is feature engineering, which consists of feature selection and feature extraction. A feature is an attribute or property of an object reflected in the data. Feature selection picks the features which are most likely to contribute to model training and prediction, and removes the ones that are not expected to have any effect on the model. By removing this noise, we can reduce overall training times, prevent overfitting, and increase accuracy. Feature extraction derives informative and non-redundant features from the existing features. This makes the dataset smaller, with the model retaining the equivalent accuracy. Exploratory data analysis helps to identify the most informative features, reflecting the trends inherent in the data. Even though the aforementioned activities and sub-activities have been shown in a logical order, real-life projects may reshuffle them, or even omit some steps. It is also worth noting that some of the data preparation steps, such as the identification, are performed just once and can be performed manually. Other steps may be part of the operational data pipeline and normally work on live data. These tasks should be automated. In order to perform data preparation, we need to know the application domain, data and its properties, plus the various techniques associated with data preparation. Then we have to consider the difficulty of getting high-quality data from multiple sources, and the complexity of automating the data pipeline. Said pipeline needs scalability and reasonable performance efficiency. These can drive up the costs associated with data preparation. The last two issues are not giving sufficient priority to checking for defects during data preparation and sample bias. Usually, 3 sets of equivalent data randomly selected from a single initial dataset are required to develop a machine learning model. They are a training dataset, a validation dataset, and a test dataset. If unlimited suitable data is available, the amount of data used in machine learning workflow for training, evaluation, and testing typically depends on the training model algorithm and the availability of resources. But sufficient suitable data is hard to obtain. So the training and validation datasets are often derived from a single dataset, but the test dataset is kept separate. The model can be influenced by the test data, and the test results have to give a true reflection of the model's quality. There is no golden rule of splitting the dataset into these three categories. But the typical ratios of training to validation to test range from 60-20-20 to 80-10-10. Data split is often done randomly unless the dataset is small or there is a risk of losing the representative quality. If limited data is available, then splitting the data into these three datasets may result in insufficient training. To overcome this issue, the training and validation datasets may be combined and then used to create multiple split combinations. Data is then randomly assigned to the training and validation datasets. Training, validation, and tuning are performed using these multiple split combinations to create multiple tuned models. Overall performance is calculated as the average. There are various methods used for creating multiple split combinations, which include split test, bootstrap, k-fold, cross-validation, and leave one out cross-validation. So by now, I think it is clear that the quality of the machine learning model is highly dependent on the quality of the dataset from which it is created. For the list of typical data quality issues relating to the dataset, please refer to the syllabus. The following categories of defects result from data quality issues. Reduced accuracy. These defects may be caused by data which is wrong, incomplete, mislabeled, insufficient, obsolete, irrelevant, and not pre-processed. For example, if the model was trained on a news article dataset with very little news about software failures, then predictions for this type of news are likely to be inaccurate. Next is bias model. These defects are caused by data which is incomplete, unbiased, unfair, lacking diversity, or duplicated. For example, if the bugs that were taken to predict fixed times were from one customer only, then it is very likely to have an adverse effect on the bug fixed time predictions for other customers. And then we have compromised model. These defects happen due to the data privacy and security restrictions. For example, it can lead to security vulnerabilities which would enable attackers to reverse engineer information from the model and might cause leakage of personal information. Now that we have sorted out possible data quality problems, let's move on to obtaining data suitable for training the model. Supervised learning requires marked up data. Data labeling enriches the unlabeled or poorly labeled data so it can become suitable for supervised learning. Data labeling is resource intensive, and it requires many resources and expert opinions. For example, experienced testers can prioritize unmarked bugs. There are many ways of performing labeling. It can be internal and done by testers or developers within the company. It can be outsourced and crowdsourced. It can also be AI-assisted and done by using tools to recognize, annotate, and cluster similar data. The results are then confirmed or perhaps supplemented by a human. And then there is hybrid approach, where a combination of the aforementioned labeling approaches could be used. For example, crowdsourced labeling is typically managed by an external organization which has access to specialized AI-based crowd management tools. It may also be possible to reuse a pre-labeled publicly available dataset, avoiding the need for data labeling altogether. And still, data gets mislabeled. This happens because random or deliberate errors may be made by annotators. It could also be because of poor instructions, bad translations, subjective interpretations, lack of domain knowledge, and defective supplementary tools. Machine learning-based approaches to labeling are probabilistic, and this can lead to some incorrect labels as well. But don't despair. Experts are investigating the problem, and there are many articles on the subject of identifying mislabeled data. And that is it for this video. If you liked it, give us a thumbs up. In the next one, we will be talking about Chapter 5 titled Machine Learning Functional Performance Metrics. As always, let me remind you that we have a ton more awesome videos on our channel, so feel free to subscribe and hit that bell button. Thanks for watching, and see you soon.